Think about a tailor in downtown Kampala cutting cloth for a beautiful gomesi, or a builder setting out the footprint for a new brick house in your village. Neither of them can afford to simply guess their measurements. To communicate true sizes and shapes, engineers, architects, and carpenters rely on an exact language, technical drawing. To speak this language, a simple school ruler is no longer enough. You need specific tools designed for perfect geometry. Learning to use these instruments with physical precision is how you take a vague idea in your head and turn it into a functioning object in the real world. This is a top-down view of the first step in any drafting project, preparing the blank canvas. You must lock the head of the T-square against the left working edge of the board. This guarantees perfectly parallel horizontal lines. It is never used diagonally. With the T-square secure, slide your paper directly under the blade until the top edge of the sheet is perfectly flush and horizontal. Hold the paper firmly in place and secure all four corners with masking tape to prevent any movement. A proper physical setup eliminates compound errors. If your starting alignment is crooked, every subsequent measurement will be wrong. With the paper locked down, we apply our layout lines. On the left side of this diagram, we have an H pencil, which contains hard graphite. On the right is an HB pencil, which is softer and darker. We use the H pencil for initial planning, drawing a faint 10mm border and a precise title block in the bottom right corner. Once we verify those dimensions are correct, we trace over the final confirmed outlines using the HB pencil. We reserve a third style, the dashed thin line, exclusively for showing hidden details that exist behind the solid object. Pencil grades and line weights are a rigid coding system. They tell the manufacturer exactly what is a permanent structure and what is just a guideline. Moving into the work area, we use the T-square as a perfectly flat base to support our vertical and angled set squares. When two drawn lines meet, they form an angle. We classify these into four foundational types: acute, right, obtuse, and reflex. Let's test this logic. If two supplementary angles share a line and one is 70 degrees, what is the other? And how could you draw exactly 75 degrees without a protractor? This diagram shows the solution to the first problem. Supplementary angles always add up to exactly 180 degrees, leaving us with a 110-degree obtuse angle. For the second problem, you can combine your tools. By sliding a 45-degree set square directly against a 30-degree set square, you create exactly 75 degrees. By applying foundational geometry, you can turn a few static tools into an infinite array of exact angles. Look at the completed layout. The perfectly parallel lines, the cleanly lettered title block, and the precise, smudge-free geometry. Because you followed the exact physical rules of drafting, this document can now be perfectly read by a metalworker or engineer anywhere in the world. This table summarizes the core vocabulary we covered today: the distinct tools, the line weights, and the mathematical rules of angles. By mastering the strict grammar of this language, you gain the ability to communicate any physical concept to the world.